And then if we need to show something that we do on the board or something else, we'll fix that. But we'll use, in fact, what we'll do right now is we'll go ahead and use this zoom tool because it's useful for doing things on. All right. So let's get started. We're going to talk about a lot of different things today. We're going to zoom through a lot of things. If you're needing some little extra clarification, then please stop me before I move on. We will go fairly slowly once we get into chapter 2 and chapter 3 and even chapter 4. But once we get beyond chapter 4, we're going to start moving a little faster because hopefully by then you've got some tools under your belt, you're a little more comfortable with the things that we're doing, and we can move faster. So let's start off here with our introduction to science, the realm of physics, physical quantities, and units. I've been told that I talk too loud and I'm supposed to shut my door, so I guess I'll do that. Probably they're just tired of looking at my message here. All right, so I'm going to sit because I carried a lot of very heavy things this morning and I'm tired. But I'll probably stand up before too long because I get tired of sitting. So physics and science, and then some more details about things like units and numbers and other things like this. I love the pictures they put in this book and other books, and physics books, because they're just interesting to talk about. In this particular picture, we have a galaxy. And yet, it actually represents, very similar to, the structure of some of the smallest things we know, like atoms. You have a central part to this. Everything is kind of centralized in this galaxy, and then there are stars that are going around on the outside. It's got a lot of fairly organized structure, but still there's quite a bit of randomness to it as well. There is a force that is holding this together, but there are also forces that are ripping it apart. And there's a big balance there. There's light, there's energy, there's heat, there's cold, there's all kinds of stuff going on, and that happens at the galactic level, and even the universal level. That happens at the atomic level and even the subatomic level and everything in between. And in truth, physicists do study all of those things. Some of the latest and greatest things that have happened in physics concern this galactic level and this universal level. Have any of you ever heard of the LIGO experiment? No? So let me see if I can remember what LIGO stands for. LIGO stands for light, something gravitational, something. No, it's the laser interferometer for gravitational something. I can't remember. Anyway, it's really cool. It's this really big. Let me actually show you a picture. We have two of them. And LIGO was the first one. The other one's called MIGO or Zygo. I don't know, something else. It's one of the big experiments in the world today. And there are usually quite a few big experiments going on in the world. It's a collaboration between Caltech and MIT. You know, Caltech is in California, MIT is in Massachusetts, and so they actually have a couple of these, but they're building more. They have some in Europe as well, and they have I think one in Asia that's being built, and they're hoping to connect these all together. The problem with looking at things in the universe is that the universe is big. And so the instruments that you have to look at the universe with usually have to be big. And we've all seen telescopes and things like this, but this is a different kind of deal. This is an interferometer. And what an interferometer does is it sends down signals of some kind, in this case lasers, that go down in one direction and then another one in a 90-degree direction. And those two directions are perfectly balanced so when the light comes back, it comes back at exactly the right synchronous moment. Okay? They balance them perfectly. And they can get pretty perfect with light. It's not that hard to get light perfect. In addition to this, you see this little like building here about halfway down there. That is actually a great big mirror that bounces the light back to where it came from many, many times, back and forth. And it makes this instrument behave as if it's many miles longer than it actually is. And it's pretty long right now. I think it's a mile in each direction or something, or a kilometer or something like that. I think it's a mile or maybe even 2 miles in each direction. But it's huge already. But then to bounce it back and forth between these mirrors, every time it bounces back and forth, it extends that distance by double, and it does it many, many times. It's a very specific, special kind of interferometer that we call a Fabry-Perot interferometer, named after a couple of scientists. And in fact, this kind of interferometer was something that I did in my laboratory on a much smaller scale, something that we did in our physics there. And we actually helped develop this. But they, of course, have taken it to a much bigger scale. What's the idea? Well, the idea is they're trying to detect gravity waves. What is a gravity wave? Have you ever heard of a gravity wave before?
Isn't it also a way to figure out if we're moving to the galaxy in a circular motion or straight?
You could use it for this, but you can use a much smaller one for that. In fact, this idea came from an experiment 100 years ago, or more, 120, 140, 50 years or something. Back in the late 1800s, an experiment was done by a pair of guys named Michelson and Morley, and they did the same experiment on a big block of probably about the size of this circle here, about 2 meters across, a big block of granite floating in a pool of mercury. How cool is that? You can float a block of, this block of granite was a foot thick, and it was in a big pool of mercury. And I like showing pictures of these experiments because they fascinate me. But let's take a look at Michelson and Morley's. There's some photographs of theirs, so not too hard to look at. So here's the basic setup of the experiment. You have a laser. They didn't have lasers 150 years ago, so they just used what we call a coherent light source, which is kind of like a really weak laser. It's essentially a light bulb that they've cut all of the color out except one color using filters, and then they shoot that one color through very thin slits so that you only get a wave going in a single direction. And then if they do some other things to it, they can also get all the waves to be moving together at one time. But it's not nearly as powerful or as bright as a laser, but it still works over short distances. But you have a mirror here that's only a half reflecting mirror, so half the light gets bounced off, goes one direction, the other half goes the other direction. And these two arms, if they're balanced just right, when these lights come back, they will both, the one that goes this way will go through the mirror, and the one that goes this way will bounce off the mirror. You're not going to get all of the light in any case, but you get enough light coming back over to the detector to tell you whether or not both arms are balanced. Now, what you were talking about is how do we know which way we're going, which way the Earth is spinning, which way the Earth is going around the sun. Well, in the direction that we're going around the sun and the Earth is rotating, of course, we're moving faster in that direction because the Earth's rotating in that direction, the Earth's going around the sun that direction. And they weren't really trying to figure that out. They knew that. But what they were trying to figure out with Michelson and Morley is whether or not the speed of light was different in one direction, going with the movement of the Earth, than it was in this direction, going perpendicular to the movement. Because according to the physics at the time, according to Newton, for example, the speed of light should be faster in the direction that you're moving. Like throwing a baseball off a train. You should be able to throw it faster in the direction that the train is moving because the train is already moving the ball that direction before you can throw it, right? But with light, that's not the case. With light, it goes the same speed this way and the same speed this way no matter who the observer is. So it's different than baseball. Light is very different, behaves very differently. And they were trying to prove that that was not correct. They didn't believe that this was the truth. And it was later on, a very famous guy, Einstein, who came along and said, I believe it. And that's really all he said. He just believed that fact, and he became the most famous and brilliant scientist of all time. In essence, that's what he said. He said it with a lot of mathematics and theory, but it was brilliant. But this experiment, the LIGO experiment, is the same thing, just bigger. It's just much, much bigger. And why? Because what Nichols and Morta were looking for is they were looking to see if light waves were traveling, different speeds. And light waves are small. Light waves that we see are really quite small. And, we're talking hundreds of nanometers small. But, to microns, they're pretty small. But if you're looking at gravity waves are miles, hundreds of miles, even thousands of miles, even maybe millions of miles long. So gravity waves are humongous. And to look at those, you need a little bit bigger instrument to be able to actually detect them. The instrument has to be kind of on the same scale. So they make this thing much bigger, but what is an actual gravity wave? A light wave is a wave of electricity and magnetism that makes light. What is a gravity wave? Well, it turns out that a gravity wave is actually a wave in space. It actually bends space. And that includes the ground, it includes the atmosphere, it includes the vacuum of space, and it includes us, and it even includes time. And light gets bent, and all kinds of matter get bent. Everything gets bent when a gravity wave goes passing by. And this is one of the predictions of Einstein, that when Einstein created his general theory of relativity, he said things that are massive in the universe create gravity waves as they move through space and time. And these gravity waves will propagate outwards from them. But most things make gravity waves that are so small and so long that they're almost impossible to detect. But every once in a while, you're going to have something really big happen out there. Something huge is going to happen, like the collision of two black holes. Black holes are the most massive things in the universe as far as we know. And when two of them collide, they create a new black hole that's even bigger. But they also create a big wave in gravity when that happens. Okay, and that's exactly what they were able to do. It just happened last year, right about this time, actually, last year. And as soon as they turned the thing on, they were just testing it. They didn't even think that they were going to detect anything, because they didn't think black holes were very common, and they didn't think that black holes colliding would be very common. If black holes aren't common, two colliding would be even less common. The very first day they turned it on, they detected two, and they've been detecting them regularly ever since. So they have discovered something absolutely mind-blowing. First of all, they're in a long list of people who have determined that Einstein was the genius of the human race. Almost, every scientist that's tried to prove him wrong has failed, and every scientist that has tried to prove him right has succeeded. Right? And it's just amazing to me to think that a guy 100 years ago could predict all this stuff and was right. He wasn't right about everything that he ever did, but his general theory of relativity has held up. Nothing has been able to break it. So, that's one amazing thing. But the next amazing thing is to discover these black holes. Black holes weren't discovered by Einstein. They were discovered by somebody about the same time, and discovered that they were theorized and then discovered later. But, to discover that there's so many of them. And what is a black hole? A black hole is essentially a really massive star that becomes so massive that its gravity sucks the actual star down into a very, very small piece. Like imagine our star being compacted into a sphere the size of our moon. To put all that mass into a very, very small space. And what happens is that all the protons and all the electrons in the star become neutrons. Become is a bad way to say we call it decay, but they go through a process where everything is turned into neutrons. And neutrons don't have any repulsive force, so they all gather together in a super tight spot. It becomes so massive that it attracts everything around it, including space, time, light, matter, everything gets sucked into it because of the strength of the gravity. And that's what a black hole is. And it turns out there's a lot of them out there. So it's very interesting. Very interesting to learn this. And, it's groundbreaking. It's opening our eyes to what our universe really is. And it's changing many things in physics. It will change many things in the future in technology and everything else as we learn more and more about it, without a doubt. So that's why I like pictures like this. That was a very long story for a very small picture. Let's call it a field trip. Come over here. Everybody up, come on, let's go. Okay, so these are the kinds of things that fascinate me when I go into physics, when I learn physics. And frankly, it's one of the reasons that I started studying physics, and it's one of the reasons that I keep studying physics, because there's just no end to it. Every day I get an email with some new physics discovery, and they're all interested. They're studying the big stuff, like the universe, they're studying the small stuff. and they're studying everything in every field. There are physicists in agriculture. There are physicists in medicine. Who's going into medicine? Is there somebody in medicine? So there's physicists in medicine. Almost every device used for analysis and whatever in medicine, almost every device, every machine was invented and developed by a physicist. Almost every single one. Yeah, I mean, you would have a hard time finding one that I couldn't connect to a physicist or something. I mean, the obvious ones, X-rays and MRIs, those were developed by physicists long before they were used in medicine. In fact, and the CAT scan and all those things, they were used in physics to do all kinds of things. And somebody said, hey, we might be able to use this for medicine. Those are obvious ones, but even things that monitor the hearts and the lungs, and if you're measuring somebody's breathing, you put a little strap on their chest. Well, all that strap is a wire that has a current going through it. And that current creates a magnetic field. But the magnetic field of a ring of current is determined by the size of the ring. So as you breathe in, that size of the ring gets bigger. And it changes the magnetic field within that ring. And as you breathe out, it gets smaller. And that is physics. And it was invented by physicists. I mean, everything, heart monitors, everything, you can't find them. Yeah, I mean, and it's not, in agriculture, they're using physics constantly these days. Agriculture was one of the later fields that physicists got into, but you could make a really good case for physicists getting into soil science very early, because they did. And that, of course, has been a huge part of agriculture, but they're getting into everything else. Since the 1950s, 60s, agriculture has been using radioactive isotopes to track their the use of plant foods and fertilizers and herbicides and everything else. They actually make the plant food and fertilizer radioactive, and then they put it into the plant, and then they can measure how far up the plant it goes by measuring the radiation of the plant. They do it all the time. It's not even uncommon practice. In fact, many people in agriculture don't even know that it's doing that, because it's so common. They've been doing it forever. And you can't, architecture, everything. Physics is everywhere. And it's not just, a little bit everywhere. It's everywhere in many, many ways. So it's a fun science to learn about. And no matter what you go and do, you'll keep learning about it, even if you don't know it. Okay, let's actually start learning something. Let's see what they have for us to learn about. Birds. Excuse me. There's some engineers who have built a robotic bee, a robotic honeybee. It's very interesting. It actually flies, and it mimics the flight of a bumblebee or a honeybee. And the reason that they're doing it is because they're trying to figure out how bees fly. Bees seem to defy nature. They seem to defy physics. But they've determined that they don't. They've determined that bees fly very differently than flies or mosquitoes or birds or anything else. Bees have a very distinct flight pattern and a very distinct wing rhythm. Their wings go, let's see, they move, I can't remember if they move faster. I think they move faster than they should. Because there are all kinds of models and equations that determine size of wing, size of animal, these kinds of things. But bees actually don't follow that model. They do their own thing to keep themselves flying. Because not only do they carry themselves around, but they pick up their weight in pollen. They can carry their weight in pollen or even more sometimes. And so that really changes things. And it's amazing that they can fly at all, but they do it. And it is not defying physics. It's just we have to learn what we're doing in physics. So it really is everywhere. GPS. Goodness, GPS was inevitable. We knew eventually we were going to use satellites to figure out where we were on Earth, but what was the biggest problem? Well, it was time. each GPS satellite has to know exactly what time it is so that it can know how much the Earth is rotated underneath it. If it doesn't know exactly what time it is, and the Earth is rotating underneath it, it will never know what's underneath it. Because the Earth is always rotating. You have to know the exact time. And it has to be within nanoseconds. It cannot, if you're off by a nanosecond, your GPS is off by a mile. Because the Earth is moving fast. It is not a slow turning Earth. And so you have to really be on time to get that right. And when physicists started developing atomic clocks, which, you know, your Big Ben in London has the tall tower. Why does it have a tall tower? What? It's nice you can see it, but that's not the reason it's on a tall tower. The reason it's on a tall tower is because it has a really long pendulum. And that pendulum is swinging back and forth, and that's how they're telling you keeping the time. That pendulum, they have all kinds of machinery that keeps it swinging back and forth. The pendulums swing back and forth at the same rate as long as they're the same length all the time. So they're adjusting its length a little bit, and we'll learn about that a little bit later. They're adjusting the length a little bit every day to make sure that it's ticking at the same, 1 time per second. But it has to have that nice long arm for it to work well. Without it, the clock doesn't work. Well, scientists, physicists, not even that long ago, maybe 30 years ago, 40 years ago, they started looking at using atoms as their pendulums, because atoms vibrate. They vibrate at certain frequencies. And it's not a pendulum really, it's a vibration, it's a back and forth. So it's similar to a pendulum. But if you can look at that back and forth vibration of an atom, they move way faster than a pendulum. So you get much more precision. Instead of taking off seconds, you're taking off milliseconds with atoms. And then they started to discover that they could actually make atoms. They could look at certain things in atoms, certain transitions in atoms, for example, like electrons go through transitions. And those move even faster, at nanoseconds. They have nanosecond cycles. And so they can control that, and they can take their information from that. It's not by any means easy, but physicists have figured it out, and that's how GPS works. And that's why it works, because we have this incredibly precise clock in Colorado, one in Colorado, one in Virginia, and Europe has theirs set. I think Europe has one in Switzerland and one in somewhere else. I don't remember. Maybe London. But and Asia has a couple of theirs because just about every continent has their own GPS system. The European Union has one, and several Asian countries have their own, and the United States has one. But anyway, the point is that those clocks were developed by physicists. Microwaves were actually developed by an engineer, but engineers are just physicists who work hard. Physicists are like physicists who play hard. Physicists get to play around with things. They don't have to actually make things that work and make things that make money, but engineers do. Here's a nice CAT scan image. I believe it's an MRI image. So it's an MRI image. You can see the eyeball there, the what do you call that? I'm sorry? Opus colossal. There you go. Blood comes up through there, right? But then you see the hemispheres of the brain. That's extremely useful in diagnostic work, right? You really need to see things. And before MRI came along, which was not that long ago, really, the only thing they could do was cut the thing open. Cut open the brain and start to turn the patient into a chef salad. And, it was exploratory surgery on the brain. It was fatal. You can't do it. You're going to turn them into a vegetable at some point, and that's just no fun. So, MRI is a beautiful tool as well as the CAT scan. And MRIs and CAT scans are kind of interesting because they're mostly computer. It's mostly about the computer side, which was developed by the physicists. The imaging side of CAT scan is just an X-ray. They just take a million X-rays from different angles and different focuses, and then they put them all together using the computer. The computer part's the hard part. The MRI is a little bit more complicated. They actually wiggle the molecules in your brain using a magnetic field, and sometimes they infuse the tissue that you're doing this with some particular chemical that wiggles better. hear it vibrates better. And they create this resonance, the magnetic resonance they call it. And then you can see that resonance as it wiggles because it creates light that you can detect. It's not as dangerous as an X-ray, but very revealing. Here they have some cells. We talked about this already a little bit. Now we talk about some of the famous physics people. Sir Isaac Newton being one of the greats and probably the father of physics as we know it today. Isaac Newton was an interesting fellow. Brilliant, crazy, and reclusive. That's not uncommon for a million people to want to be alone. They have a tendency to like to be among people as brilliant as they are, so they have a tendency to be by themselves a lot, right? And he did not like other people for a lot of reasons. One was because he was just so stinking smart that nobody understood him. But the other one was that he didn't think the world was worthy of his ideas. He didn't want to share his ideas with the world. But he was also very jealous. He was jealous and he was very protective of his ideas. So when some Germans came along and started figuring these things out a few years after he had it, he immediately came out and published his works. The Germans were working on calculus. Newton, of course, was not just working on calculus, but everything that calculus can do. But these Germans came out and said, we know how to figure out calculus, and Newton says, I figured that out a long time ago. They're the Leibniz brothers, I think, the two brothers, Leibniz. But what we do have from Leibniz brothers is we use their little curly thing when we do an integral. We use their notation. We don't use Newton's. But Newton figured out everything to do with motion, pretty much. He published the first textbook on physics. If it has something to do with things moving, Newton's our man. If it has something to do with what causes things to move, Newton's our man. He figured it all out, and a lot more. He worked a lot with optics and light. He worked a lot with heat and energy transfer. But he was also a religious person, but also involved in the occult, and he was into superstitions. He was very much a man of his day back in the 1600s. The 1600s were a day of superstition. Another interesting thing is that one of my ancestors, Philip Packer, knew Newton, very likely, because they were in the same club together. I love mentioning this because it connects me to Newton. So I always spell his name wrong. Here's Philip Packer. This is Philip Packer Sr., I believe. This is Philip Packer Jr. He had a son and a grandson named after him, I believe. Isn't that a great wig, though? I just love that wig. He lived in the early 1600s, and in the early 1600s, the Royal Society was begun, which was the first scientific society in the world, as far as we know. The first group of people that got together to share ideas, to trade research, to collaborate with each other, to work together, and to make sure that science was being recorded and done well. And way back in the 1600s. And at that time, my ancestor here, Philip Packer, was an architect, built his own castle. This is his castle right here that he built. It has a moat and everything, a moat and a drawbridge and all these things. Pretty great. I wish that I'd owned it, but some rich American bought it not long ago and sold all of the family heirlooms inside the castle off to the highest bidders and just lives in there in a modern looking inside. It's kind of sad, but anyway. I wish I could have gotten this painting from the auction, but it went for like $2 million or something. My parents have the auction book. But anyway, the point is that there were many great scientists in the Royal Society over the years, Newton being one of them. Right as Philip Packer was near his death is when Newton was inducted as a member. So they had a layover there for about 3 or 4 years in the same club, in the same Royal Society. And the reason it was called the Royal Society is because scientists at that time were mostly wealthy, royal people. They were mostly people that had some kind of knighthood or some kind of lordship or whatever in a manor and a castle. And they were all, going to the king's court all the time. And they had money and time. So they could be scientists, Scientists back then, people back then had to work for a living 24/7 pretty much. They were just constantly working, and there was no time to be a scientist. But rich people who were taking money from all those poor working shops had all kinds of time and money, so they did all the science. And that's the way it was for many, many hundreds of years. And it's kind of a waste, I think. I think there were probably many great minds among the common people, as they were called, that were never developed, and we probably could have developed faster if we behaved differently. So there's Isaac Newton. Marie Curie, of course, famous for being a scientist in the early 20th century, was a woman, which was rare then. But let me show you something even more rare. See if I can find the right poster. This one's pretty rare. This is on 1844. Ada Lovelace, 1844. She was a scientist who actually figured out computing. She figured out how to write computer programs before a computer even existed. She was writing computer programs. She was figuring out algorithms for solving mathematical problems. And almost everything that we do with computers today is based on her work. That's amazing. They did. They did. And then there's another one. I have a poster of actually up online. And the reason I mention this is because science was the realm of the rich man for so long, but there were some women that snuck in, and they were, I would say, they were brilliant, of course, to even be recognized as a scientist, and many of them were during their lifetimes even. But to have that, but they were kind of brazen too. To break those social norms at that time was just unheard of. So they had to have some serious guts to do this. The other one is named Marie, no, not Marie, Châtelet, du Châtelet. She's French, of course. Émilie du Châtelet. I always want to say Marie, but Émilie du Châtelet. This woman from the 1700s was brilliant. She actually took Newton's work. There was a lot of arguments about Newton's work after Newton. And the argument was about what is energy and what is momentum. These two things that they came from Newton's work, called energy and momentum. They were very similar to each other, but there was an obvious difference. But nobody could really figure out what was the difference, and nobody could really figure out why there was a difference, and nobody could define what they really were. She figured it out. She did experiments, and she figured it out. Now this is 1749. Women were supposed to be sewing. Women were supposed to be looking pretty and dainty. They were supposed to faint if something surprised them. All these things. If you ever watch those Jane Austen movies with your wife or girlfriend or something, I hate to be sexist about that, but not very many men like them. I actually do. If you watch those Jane Austen movies or read the books, the characters are hilarious. Jane Austen was a brilliant writer. But anyway, the point being, if you've ever watched those movies, that is that time period, and that is the way people behaved. That's a little bit later, but it's the people, the women were expected to be sewing in the afternoon, or daintily reading an innocuous book that's not inflammatory or anything, poetry or something. And there were many women who broke that mold and started this revolution of getting into the sciences and the mathematics and other things like this. This is her book, Principiis Mathematiques. But she actually did this, and she did it with the help of her father and brothers. Her father and brothers were scientists, but not nearly as talented as she was, and they knew it. And they published her works under a pseudonym for her. so that she could be published. If they published it with her name, nobody would have taken it. Nobody would have published it. And they weren't doing it to push her down because they were encouraging her and they weren't trying to take credit. But in the end, they were able to get her started on her own path scientifically. And you haven't heard of Voltaire, the great philosopher, writer, right? Best friends with Voltaire. In fact, they had a little bit of a thing going on. She was married to some, rich putz that was an idiot. But Voltaire and her, they got along well, as the stories go, and lived together actually for quite a while as well. So she was in good company with the brilliant geniuses of the day, the men who respected that. Voltaire is certainly a genius of the day. So a scientist well beyond their time, not only scientifically, but socially, which is important. It is important to break social norms because social problems in this world cause scientific problems. And that's a big theme of mine. We have more than our fair share of social problems now that are causing scientific problems. As many as they had then, they're different now. They're different now than they were then, in some ways. In some ways, they're the same. We still have sexual politics in science. I mean, and who wants to be an engineer here? Who's interested in engineering? No? Interested in engineering? I guarantee you, you go to an engineering department and you take your first engineering class, there are going to be 400 men and 3 or 4 women. You know? My friend used to joke, I had a friend who was a girl, she was in the physics department, and she was dating a guy in the engineering department, and she took a class in the engineering department. When she came back from her first class in the engineering department, I said, so how was it? She said, well, if you're a girl in the engineering department and you're looking for a date, your odds are pretty good. You got all these guys, but the goods are odd. The engineers are a little weird. She married that guy. So tell me a little bit about her. She was a little odd too, but she was also brilliant. Anyway, so women in science, it's something that we often think of as just recently, but not so. There were many, many courageous and brilliant and hardworking and people that weren't afraid to break the social mold out there, that both men and women, that helped that come to pass. So now we're going to talk about some things that you've probably heard in other science classes, but physicists have a tendency to think of them differently. Now this seems like a lot of just talking, but it's important to start thinking like a physicist in this class. When you go into a biology class or chemistry class, they have very specific ways that they define things like theory and the scientific method. That's my favorite one. The scientific method, if you go into biology class, is a very different thing than it is in physics. What is the scientific method about? Do you guys remember how it goes? I can't remember. It's like there's a problem, and you make a hypothesis, right? And then you test your hypothesis, and then you do what? Analyze the results, and you create a new hypothesis or something, and cycle repeat, right? So that's kind of that's the accepted thing in biology, they do it in chemistry, they do it in a lot of places. And it's fine, it's a good method. But it's totally different than physicists. You do have to be a little more fluid, but also we have a tendency to think in terms of observation first. We don't necessarily think of a problem. What's the physicist's problem is the universe. We don't understand that there's a problem. Okay. We've got our problem. Where do we go from there? In physics, we have a tendency to observe. And observe. And we look for things that we can't explain, that are just true, but there's no explanation for it. Okay? And we create laws around those things. So one of the laws that you're probably familiar with is the law of gravitation, right? When Galileo started making these laws, he made a law of gravitation that said gravity pulls things down towards the Earth, and it pulls everything at the same rate towards the Earth. So everything falls with the same acceleration. Doesn't matter what the mass is. If you have a heavy thing and small thing, drop them, they fall at the same rate, they hit at the same time. It doesn't work so well with feathers because feathers float in the air, they have that resistance in the air and stuff like that. But small things, big things, doesn't matter. So I got this very small thing, I just picked it off the floor. It's a small BB, which is the size of my Pluto in my solar system. Just this little tiny thing. Did I tell you guys about my solar system? No? I made a solar system in North Platte. The sun, okay. Well, I lost Pluto. Right? Oh, good. Sun is better as mine. Hard to pick up. So the sun is 6 feet in diameter. It's over here, and Pluto is at the park over by Cody Park. So there's Pluto, and here, this would be about the size of Neptune, maybe. A little big. Neptune's a little bit. But if we drop them, neither of these things has much air resistance. We drop them. It goes a little bit, not a little bit late, it's like my finger. I have to figure out a better way to drop it.
How to do the video with the feather and
The feather and the hammer on the moon.
they set a feather and hold on the vacuum chamber.
Yeah. No, look this way. Right? They both fall at the same rate, they both hit at the same time. And of course the masses are very different. And you can, and they did that on the moon. In fact, I can't remember if I think it was Buzz Aldrin who did it. The first landing on the moon, they took a feather and a hammer and dropped it. They fell at the same rate at the same time. But that's a law. That was a law that was unexplained at that time. Newton came along and explained it later, and he made a new law called the universal law of gravitation. But there were still some things that weren't explained. They didn't know why masses attracted each other, but they knew that it was true, so they made a law. And that's what physicists do. Physicists first observe things and make laws. All the things that you can't explain, that have there's no way to say why they happen. You just say that they happen, and you explain how they happen, not why they happen. If you can't explain why, just explain how and make it a law. They call that axiomatic. It's something that is an axiom, is accepted as truth, even though you can't explain it. Okay? The human race has lots of these kinds of things in our history. But in science and physics, we have to have those because if you can't explain it, you don't want to waste time trying to explain something unexplainable. And hopefully, as you move forward, you'll find something that will help you explain it, and then you can go back and explain it. And that's kind of where we're at. Then, once you have those laws in place, you use those, and those laws are usually described mathematically as well as in some kind of verbal sense. But once you've explained those laws, as well as you can mathematically or describe them anyway, and created these laws and established them, then you can create models or theories based on these laws. Now, what is the difference between a model and a theory? A model is some kind of structure, usually mathematical in nature, that starts to use the laws that you've established to explain other things that happen. Okay, so you've got these laws that you're accepting as truth, and you use them as you can, if you can, to explain other things that are happening in other situations. And these models create kind of a structure, right? All these different equations we put together create a structure we call a model, actually. And the model then is tested by experiment. So you've got this model that you think describes what's going on, explains what's going on, and you start testing it. You do experiments. And that's where that normal kind of thing fits in, the normal experimental process fits in that you've learned in biology. From that point, you can say, here's the problem, here's our hypothesis, we're going to do this experiment, we're going to analyze our results, and we're going to test and we're going to see if it fits our model. If the results fit our model, then our model is good. And we keep doing it, right? So that's a model. And so most of what we consider to be scientific knowledge today are just models. They're models that we're testing. We're still testing them. And there are no scientific models out there that are completely, flawless. At some point, we're going to test something in every scientific model. We're going to find a mistake and we're going to fix it. And that's what science is all about. We're going to fix the model, make a new model from our experimental results, And then we test that model, and we just keep pushing models outward and making them bigger and more detailed, and learn more and more and more. Now, a theory is a little bit different than that. A theory doesn't use the actual science to test the model. Okay? A theory is where you're using mathematics and logic to push the model outward theoretically. You're pushing the model outward mathematically without checking it in science. Now, why would you do that? Why would you create a theory without testing it and making it a model? Might not be able to, right? There are often models that we want to create, but the laws that would support this model have not been discovered yet. So if you don't have any laws to support your model, you have to make it a theory, right? And sometimes there's no experiments to test the model. So the model is not actually a tested model, it's actually a theory. And that's
quantifiable
exactly.
known.
What's that?
It's a quantifiable known, and they're already doing stuff past it.
Yeah, that's correct. If you've got a model that has been tested and you're pushing the boundaries outward without experimentation, without confirmation, then that's theory, right? And we do that all the time in science. But the differences are subtle. You know, people who are experimental physicists are testing models and correcting models and changing models and expanding models. But they're pretty much hands-on people. They're doing a lot of experiments and they're analyzing a lot of data. Where theoreticians are generally sitting at a desk and a computer, you know, in a dark room all by themselves, and they're and thick glasses. And don't want to be too stereotypical, but it is actually kind of true. These people have a tendency to be kind of introverted. They're thinking, they're inside their minds all the time, they're inside other people's minds all the time, and things are just clicking in there, and maybe they don't even care what the experiments are. It happens all the time. There are many physicists and scientists all over in many fields who do both, who are experimentalists, but they're also theorists. And that's actually the most common, is a little bit of both. But there are definitely people that spend time with one or the other. A good example of this is out at the farm here across the street we run out research on. We have mostly experimentalists. Most of those people over there are out in the fields, planting crops, digging up samples, measuring moisture and all this stuff. That's experimental work. But there's a couple of people out there, in particular I can think of one, who is his specialty is agroeconomics. And all he really does is create theories about how the economics work with agriculture. He creates these new theories, and they do compare them to models. They have models that come from the actual what happened last year. They take what happened last year and they try to match it to some mathematical structure, and that's a model of what happened last year. But then they try to take that model and they try to expand it into a new theory of what might happen next year. Because agriculture is a very, very complex thing. All kinds of things coming in, going out, money and materials and product and everything else, in and out, and the international market affects it, and the commodities market affects it, everything affects agriculture, the rain and the sun and all this stuff. And all that has to be put into some kind of theory of what's going to happen next year. And it's important. How much money is made by a farmer who knows what's going to happen next year?
Yeah.
And how much money is made by a farmer who doesn't know? Well, who knows? It might be a lot, it might be a little, but on average it's going to be pretty low, right? And so they spend a lot of time on it. They're tracking weather, they're tracking markets, they're tracking everything. And they're putting together models and they're expanding those into theories, and that's what he does. He spends most of the time on a computer, just creating these theories. So, lots of that going on all over in science. Models, theories, laws, axioms. We need to understand them because we're going to use them quite a bit. Notice here that our scientific method in physics doesn't have a list of things. We don't have the create a hypothesis. It's just kind of a couple paragraphs talking about that stuff. Here's one of my favorites. Aristotle. Usually thought as a philosopher, but also great theoretical scientist, a great experimental scientist. Back in the Galilei, he's the one that started the research on gravity in Europe, dropping bowling balls out of the Leaning Tower of Pisa. I've always wanted to go to Pisa just to drop a bowling ball out of
Probably long.
Oh, they'll let a foreigner get away with it, wouldn't they? Italians are nicer foreigners. Niels Bohr, anybody know what he did?
That's why we drink from heavy wine.
Niels Bohr was famous for developing the model of the atom that is most often thought of today, which is this atom that has electrons that are in the space around it in kind of these clouds, as we call them. Niels Bohr figured out that the energy levels of the electrons are what determined their nature rather than distance or speed or anything else. It's just the amount of energy. That's very interesting and very important. He took what we think of now as classical physics, Newton's physics, and he changed it into a statistical kind of physics involving things that we can't see and behave statistically rather than linearly or continuously. Something we would learn about in our second semester. And right here is some of the results of his theories that have become models, and there's still a lot of theory to them as well. One of the other reasons for having theory is we mentioned there's no way to test it, no way to experiment on it. Well, a lot of Niels Bohr's theories can be tested, but they can't be confirmed in a. We can't confirm them personally, I guess is the best way to say it, directly. We cannot see, quote unquote, an atom. It's impossible. I'm not just saying that it's, it may be possible someday. I'm saying that it is absolutely impossible to see an atom. A single atom is smaller than the wavelengths that we see with. It'd be like trying to detect a mouse using an aircraft carrier, right? You'll never see the mouse. It'll just get squished. It'll never be, you can't do it. It's like trying to catch a trout using an aircraft carrier as your fly. It's just not going to happen, right? The trout is the atom, the aircraft carrier is the light that we use to see with. So the only thing that we can do to see the atoms, quote unquote, is to detect them using secondary methods, using other things that we can detect, things that can detect the atom that we can detect. So we're seeing, it's like, it's like talking to your best friend about their best friend that you've never met, and that person that you've never met is going to be your best friend through your best friend. Right? That's how we do atomic physics. Another way to think about it, my favorite way, is pinball machines. How many of you have actually played a pinball machine?
Oh, I love you.
Pinball machines are great. You know what we're talking about, pinball machines? Yeah. Right? So you're playing this big pinball machine, it's all complicated, crazy angles and everything else. Now paint the top of it black and play. That's what studying atoms is like. All you can see is the ball coming down here, and that's it. And maybe you don't paint the edges, so maybe you can see when the ball hits the edge, but you can't see anything that's happening inside here. That ball is a particle that can detect an atom, and all you can see is what happens when it comes out of the atom or away from the atom, and when it does something to one of your detectors. That sucks. And they've actually figured it out. The job that they have is 1,000 times harder, and they've actually got great models that have held up to the test of many, many experiments over, we're talking trillions of experiments over the past 100 years. So that is brilliant. Niels Bohr was brilliant, and many of the scientists since then have been brilliant as they've tried to figure out new methods to detect these things. So this is one of those devices that's used. It's called scanning tunneling microscope. And what it does is it puts electrons that are very focused and that are going in very straight lines, and it shoots these electrons at a material, And as the electrons will actually go through the material, because to an electron, a bunch of atoms is like a forest, right? It's just like a forest, because the atoms have these nuclei, but around the nuclei is just open space with some electrons. So electrons can go through all kinds of materials, including gold, which is, I think this is, yeah, gold. So electrons can go right through a sheet of gold, and what happens though is they go through the gold, it's like going through a forest. Every once in a while, they'll get close to a tree, and they like trees. Electrons like the nucleus. And so they kind of get closer to that tree, but they're going so fast that they never hit the tree, well, not never, but they rarely hit the trees, they just kind of turn when they get next to the tree. And as the electrons come out the other side, you can see a pattern from all the turning. And that pattern can be created, you can create that into an image.
So where the tunneling like
Yeah, the tunneling is the going through, and it's tunneling is a little more than going through. To explain that would require a little bit more quantum mechanics. More what it is it actually it meets this energy barrier and then it goes through it without actually going into it. It'd be like you going through that wall without actually ever being inside the wall. You were here, now you're there, and that's called tunneling. But in the meantime, you are affected by that movement, and then you can use that effect, the effect to make an image. Tunneling is a lot more complex than I'm making it sound. It's not actually going through something because there's no evidence that electrons actually go through things, but they do end up on the other side somewhere. We've never been able to find evidence that they're actually inside or anything. So what we say is that we call it tunneling, but really it's kind of a quantum leap. You've probably heard that term before. That's exactly where that term comes from. It was used originally, but then that confused people, so we call it tunneling to make people less confused. Physicists do that a lot. We're just like, oh, that doesn't make sense to you. Well, we'll change the name, and it'll mean the same thing, but now it'll just, you'll accept it.
Because an atom is porous, right?
I'm sorry?
An atom is porous.
Porous is a bad word to use for an atom because we don't really know. We can't see an atom. We have ideas of what it is, but we can't see it, and we can only use indirect methods to measure it. And so they don't have any evidence that shows that it's porous necessarily, or anything like that. There's no evidence for that. But there is evidence that all of the mass is concentrated in a very small point. There is evidence of that. There's evidence that the rest of it is pretty much empty space, but there's not evidence that things can go through, that things can be inside. Something that's porous, things can be inside. But we haven't been able to detect anything being there. We've detected it being on one side and then the other, which suggests that it went through, but we can't assume that because we don't have the evidence. If you assume it, then all kinds of things fall apart in the model. It's really weird, but the way they've gone about it is very scientific. So they never assume anything that they can't confirm. If you can't confirm it, it doesn't happen until you can confirm it. And that's the brilliance of this, is that we have a model that makes no sense on our scale to human beings, but it makes perfect sense to what we're observing. So it is as scientific as it can possibly be. And people say that science is based on fact. From what I've told you so far, is there any basis of truth in that statement, that science is based on fact? No. Science isn't based on fact. Science is based on laws, which are assumed to be true, models that are wrong all the time and we have to fix them, and theories which we can't prove at all. That's what science is based on. There's no fact there. There's no fact at all in science. In fact, if there was, it wouldn't be science. We wouldn't have anything to learn. There's no fact in science. Science is based on nothing but supposition. We assume things and we go from there, and then we find out we're wrong and we assume new things. And we go from there. And we do it ad nauseum. We'll be doing this forever. We'll never figure it all out. Which is kind of fun, right? I love it, and even scientists say that science is based on fact. I could never believe in this, because science is based on fact. Would you believe it that half of scientists in the world, or more, it's actually considered to be more than 60%. 60% of the scientists on Earth today are religious, and devoutly religious. They truly believe in God, they truly believe in things that we can't explain. But after this, can you blame them? It makes perfect sense to believe in things that we can't prove. Especially if you have some kind of experience that gives you some evidence of it. I was born into a religious family, and I am a religious person, and I have many personal experiences that have backed that up. And I have absolutely no proof of it for anybody, but I don't need to prove it to anybody. Just like I don't need to prove physics to anybody. If they want to learn physics, they need to take the class. It's the same with religion, in my opinion. If you want me to prove religion, take the class. Go to church. Go to read something religious and search it out for yourself. Because physics is the same way. Nobody will be able to just tell you physics is true. Because it requires that you learn it yourself. Okay, so we've gone through enough of the philosophy. Let's move on here a little bit. Now we're going to start getting into the nitty-gritty. Don't worry, I will still wax philosophical from now and again. You'll have a chance to dig in that. So this right here is a very apt picture for us right now, because we just had the eclipse, and of course the Earth and the Moon, and the distance between the Earth and the Moon, and the Earth and the Sun makes the Moon look the same size as the Sun in the sky. So they're almost exactly the same size in the sky, even though they're very different in size and in reality. But that's the reason that the Moon can actually block out the Sun. And it's a very interesting coincidence and a very cool one to see if you see the eclipse. But this picture is actually even more interesting, taken by the Apollo spacecraft. I don't remember which one. I think Apollo 8. I think it was Apollo 8. I think this one was taken before they landed on the Moon. So the Apollo 8 was the first one to go around the Moon, to orbit the Moon, and then came back. And I think that this one was taken by Apollo 8. It was the first Earthrise seen from the Moon, and it was published live. This was transmitted live to Earth in color at that time. This was in the 1960s, the mid-1960s, late 1960s. I think it was 67 or something like that. I don't remember when the moon landing was, but anyway. It was mid to late 1960s. This was the first time that the human race saw the Earth as a single object in the sky. As just this tiny little ball. Instead of this big flat Earth that we live on. Instead of a whole bunch of countries connected by politics. As a bunch of continents separated by oceans. You know what happened in the 1960s as well? All over the Earth, except in a few places, but even in places like China that were pretty closed off, the Earth, the world, started to change. It started to change socially. For the first time, human beings saw their planet as a small little dot in this huge, expansive universe, and thought, you know what? Maybe our problems need to be fixed. Maybe there's something bigger than us out there. And the civil rights movement began. And the sexual revolution began. And countries stopped being so warlike with each other in many parts of the world. There were many wars that were about to happen at that time, and they cooled off a little bit at that time. The Cold War was taking off pretty hard, that's for sure. So there was certainly some problems still on the Earth. But it was ended within 20 years of this. Within 20 years of this picture, it was over. And there's still problems on the Earth, but we're figuring out slowly how to fix them. Some people didn't see this picture obviously. There are some people that never got the message. But Europe before this was post-World War II, struggling. The United States was a mess of social problems. South America was war, 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 war. Southeast Asia was war, 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 war. And with 10 to 20 years after this, a lot of that was stopped voluntarily. It didn't just cool off. It was stopped on purpose by people who wanted to stop it. Even China, who was, who was looking like to be the next great power, the biggest country on earth, this communist thing, Russia never really had the ability to become the big power because they didn't have the resources. Their job, what they tried to do was go and steal resources from Eastern Europe. And it didn't work out so well. Eastern Europe wasn't happy. So they broke up. But the Russians fell apart because they had no resources. But the Chinese had resources. And they had a lot of people. And it seemed like they were going to be the next power after Russia fell apart. And they've become, they're powerful, but they've become more of an economic thing than a military thing. And I don't know if that will change, I hope not, but I'm okay with having a big economic power in China. It's good for everybody as long as they treat their people okay, which they're struggling with. But it changed a lot of things. And it was physics that got us there. Physics and physicists. So, how are we going to get places in physics? How about that segment? We're going to get there by measuring things. When we measure things, we need to know how are you measuring them, so we're going to use units. The unit system that we use is called the Système International. It is French because back in the 19th century, France was the center of the scientific world at that time. Mostly because it's kind of in the middle-ish of Europe, Western Europe, and Western Europe was a big center of science. Einstein was there, many other great scientists were in Europe at that time, in the early 20th century. So it made sense that we would center it on France and Switzerland, and Switzerland was a big part of it as well. But, French is the language of both those countries, and so everything was done in French. Then we have a lot of French words that we use in physics. We get used to it. We also use a lot of that. Here's atomic clock, by the way. Looking at it from the top, it's called a fountain clock. It's like 12 meters high, actually, 7 meters high. But the units that we're going to use are this international system of units. And for length or distance, we're going to use the meter. That is the standard unit. Now we also break it up into smaller pieces, like millimeters and centimeters. And we, make bigger ones like the kilometer. But the meter is the standard unit. So whenever you are using measuring length or distance, you want to convert it into meters. If it's in feet, convert it into meters. If it's in kilometers, convert it into meters. And that's the general rule. We're usually going to do that. Now for mass, which of course is different from weight, what's the difference between mass and weight?
Mass is size, weight is how much.
So, go ahead.
Mass is physical.
It's stuff, matter, right? Yeah. So, and you said?
Mass is size, weight is power, density.
Okay, that's a little bit close, but it's a little ambiguous too. What we're going to say is that mass is how much stuff there is. Now, size can depend on the density. It's actual size. But it's just how much stuff, how many, you could say it's how much matter there is, or how much atoms there is, how many atoms there are. You kind of think of it like that. But it's how much stuff there is, And that is what mass is. So your mass never changes as long as you don't lose any matter or gain any matter, right? If you don't lost any stuff or gain any stuff, your mass stays the same. My mass on the moon, if I went to the moon right now, would be the same as my mass on Earth, but my weight would be much different on the moon. Why is my weight different on the moon than it is here? Yeah, the moon pulls on my body less because it has a smaller mass itself, and it has less gravity. When else is our weight different? Here on Earth, when does our weight change? Besides losing weight. Okay, if you go up to the top of Mount Everest, you will lose weight. You'll lose weight because it's a really hard climb. And once you get about 20,000 feet, your body starts to die. But at the top of Mount Everest, which is like 9,000 meters high, it's further away from the center of the Earth, and gravity is pulling on you that side. So you lose a few ounces, not very much, but it's a little bit. When else can this happen? How about an elevator? You lose weight in an elevator?
Now you gain it.
Well, you lose it at one point, and you gain it at another, don't you?
Yeah.
When you first start going down an elevator, you lose weight. And if you put a scale in the elevator, you can actually see it. Stand on a scale in an elevator, push down, your weight goes down when it first starts, and then it goes back to normal for a little while. And when you get to the bottom, what happens? Your weight goes up. Right? So you lose weight and then you gain weight. It's not a very good weight loss program, but it's just about like every other weight loss program I've tried. Right? You lose the weight and then you gain weight. But anyway, so that's what the kilogram measures is mass, not weight. It actually is a measure of how much stuff. Okay? Here they show a nice little graphic. Light travels 1 meter in point. Let's see, what is it? 1/300 millionth of a second, right? It travels 1 meter in 1/300 millionth of a second. That's actually how we define this, a meter nowadays. That's how far light travels in that. Okay, so those are the basics. The one for time is going to be the second. So for here it is. They said this up here. So the standard unit for time is the second. The standard unit for length is the meter, and the standard unit for mass is the kilogram. Those are the three that we're going to start with. Almost every other unit we'll use will be a combination of these later on, because you can combine these. For example, meters per second. Meters divided by second gives you velocity, gives you speed, right? So you can have other units, but they're usually made from these three units. And these units come from a system we call the metric system. And the metric system divides things into what? In the English system that America uses, we divide things in, the foot into 12 parts to get inches, and we divide we divide the gallon into 16 parts to make cups, and we use all these stupid divisions. But in the metric system, we divide everything into tens, right? Tens, hundreds, thousands. So it makes sense. You have 10 fingers, 10 toes, unless you have an accident, and it makes sense. It's also easier to do the math. The only one that is not divided into tens is the second, right? The second is, we're still using the what is this? The hectadecimal system of the Egyptians, or whatever. So anyway, sextodecimal, whatever. So we use these prefixes to determine what we're dividing by. The ones that we use pretty regularly are right up here in the middle. So if you're not dividing by anything or multiplying anything, of course you're not using a prefix, it's just the meter, for example. But if you divide by 100, divide a meter by 100, then you get a centimeter. If you multiply a meter by 1,000, you get a kilometer, right? And those are what we use for meters. We use kilometers, meters, centimeters. We often use millimeters and micrometers and nanometers, even peak meters sometimes. But we don't often use the decimeter. That one's not used very often. We don't use the decameter or the hectometer very often. Here we do use the hectare, right? We use that one. That one's 100 acres, right? In Nebraska. But depending on the unit, we use different things more often. For example, with the second, we almost never use a centisecond, but we often use milliseconds and microseconds and nanoseconds. But we almost never use a megasecond. But we do use megameters or megajoules, or here they're using megacurie, which are curie. But megacuries measures not really used. So those are things that's a thing to kind of keep in your mind. If you're using one of these prefixes, this is what you multiply by. So micro, you multiply by 10 to the minus 6. And 10 to the minus 6 is, of course, dividing by 10 to the 6, or dividing by 1,000,000. Here is the shorthand that we use. Micro uses a mu, which is a Greek letter. Milli uses an M, so millimeter. Centimeter is, the centi uses a C, and so on and so forth. We show all these here. Well, here, terawatts, right? Gigahertz, gigabytes uses a capital G. for the abbreviation. And then they tell us some, they give us some what's the word for it? I can't remember. But anyway, they give us some examples. Ice in the Antarctic Sea, this is phytoplankton swimming among these crystals. So this is a phytoplankton. And these are the ice crystals in here. And that is measured in millimeters in length. So 2 millimeters maybe as these can get to. Ice crystals are right around from a millimeter to a centimeter big. So we're looking at millimeters. Here we're looking at galaxies. And this is a collision of 2 galaxies. And we're looking at, what's the size of this? Well, 2.4 billion light years away from Earth. Well, a light year is the distance that light travels in a year. And considering that light travels 300 million meters per second, and there's a lot of seconds in a year, many millions of seconds in a year, it gives you an idea of how big this distance is. So it becomes quite large. Now, let's talk about conversion. This may be reviewed for a lot of you, but let's talk about it anyway. When you're converting from one unit to another, first of all, you have to realize that you have to convert like units. Units that measure length can be converted. But you can't convert a length unit to a mass unit, right? So make sure that your units match when you begin and when you're done. But whenever I'm doing math with units, I like to use this format that they're using, which is this, where you have these fractions that are with this horizontal line. Some people like to put that line that's at an angle or whatever for their fractions and for their units. But I like to do it this way, because it shows you very explicitly what's canceling out. In this case, we have 80 meters that we want to convert into kilometers for some reason. And so we use what we call a conversion factor. Now, a conversion factor is equal to the number 1, always. You have this thing in the top and this thing in the bottom, and they are equal to each other. 1 kilometer is equal to 1,000 meters. So you're multiplying by the number 1. When you multiply by 1, what do you get? Whatever you started with, right? So it doesn't change what you got. It's like changing your clothes without changing the person, right? So we haven't changed anything about this number 80 meters, but we have changed its units. We haven't changed anything about its actual value. But notice that the meters here and the meters here, one is in the numerator, one's in the denominator, so they obviously cancel. That's what's important, because it's easy to get this thing backwards. What if you put the 1,000 on top and the 1 on the bottom line? And you thought you were right. Well, you're going to get the wrong answer over here, right? Because here we're dividing by 1,000 to get the conversion. And if we did it backwards, we'd be multiplying by 1,000 and going the wrong way. So whenever I'm creating my conversion factor, I always put in my units first. I won't even put the 1 and the 1,000 in. I'll just put 80 meters times kilometers over meters. I put the thing that I want on the top and the thing that I don't want on the bottom, because the thing that I want to get rid of is on the top of the unit. And then I can see the meters cancel out, and then I just fill in the 1,000 meters per kilometer, or 1 kilometer per 1,000 meters, however you want to think about it, and then just do math. It's that simple. Here they've got this link for lots of conversion factors. It's in the preface. So they have a lot of conversion factors listed somewhere. Nope, not listed. Useful information probably. Units. British means outside units. So the units and conversion factors. So these are conversion. These tell you conversion factors. For example, there's 1 inch for every 2.54 centimeters. So if you want to make a conversion from inches to centimeters, then you need to put 2.547 divided by 1 inch will equal 1, right? So these are all your conversion factors for different things. And it has combined units as well. For example, force is a combined unit that involves meters and seconds and kilograms. But here you're converting a force in pounds to a force in newtons. Pounds is the thing that measures weight, and weight is a force. So all these conversions here are related. Now, let's go back to our word, which was here. No, let's just do it. The internet is slow, obviously. That is not the. Let me go back this way. Okay, so you're in 3.1.2 looks like. Physical quantity in units. Okay, so let's do an example, our very first example. Woo! We're going to convert. We're going to make a conversion. Suppose that you drive the 10 kilometer from your university to home in 20 minutes. Calculate your average speed in kilometers per hour, meters per second. And note that the average speed is the distance traveled divided by the time of travel. So we're giving you some quick physics lessons. Average speed is distance divided by time. So what we want to do first is take the information they've given us, which is kilometers and minutes, and do the math, right? So we take the 10 kilometers, which is our distance, divided by the time, 20 minutes. You get 0.5 kilometers per minute, which doesn't happen to be any of the things they asked for. Right? Calculate your average speed in kilometers per hour and meters per second. So we don't have anything that they want from us. But we can convert, because kilometers per minute can be converted into kilometers per hour. We just have to convert that minutes into hours. Now notice that they're using this fraction for their units that has got this horizontal line, so it's not confusing, and it's kilometers divided by minutes. And we want kilometers divided by hours, so what we want to do is get rid of the minutes. So I put in my conversion, I want minutes on the top so that they'll cancel, and hours on the bottom, so I'll end up with kilometers per hour. And then once I know that I have minutes on the bottom and minutes on the top and hours on the bottom, and I know there's 60 minutes for every hour, I just put the 60 on the top, because that's the minutes, and the 1 hour on the bottom, and that's the same amount of time, top and bottom. This number is equal to 1. So it's not going to affect my 0.5 over here, except to change the units. It's not going to affect the speed, rather. It will affect the 0.5. It won't affect the actual speed. It'll just change it into a different set of units. In the end, your minutes cancel, and you have 0.5 times 60 kilometers per hour. Now, if you had a different number down beside the 1 down here, you'd also have to divide, but we don't. We just have 1, so we're good. So we end up with 0.5 times 60, we get 30 kilometers per hour, is the same as 0.5 kilometers per minute. Right? It's like if you do this in miles per hour and miles per minute. You know, most people have learned through driving for many years that 60 miles per hour is the same as how many miles per minute? 1 mile per minute, right? That's exactly what they've done here, except they do it 30 kilometers per hour. So it's not any different. Now, if we want to go to meters per second, we're going to have to do 2 conversions, right? We're going to have to convert our meters and our kilometers rather and our hours. So we do 2 conversions. There's 1 hour for every 3,600 seconds. The hours need to cancel, so in my conversion, I put the hour on top because in my original number, my hours are on the bottom. Then I plug in the numbers, and I end up with kilometers per second when I divide 30 by 3,600, doing that math. Then I convert the the kilometers into meters, and the kilometers are on the top here, and I want to replace that with meters, so I put my meters in the top, put my kilometers in the bottom of my conversion, so they'll cancel out. And if the kilometers cancel out and the hours cancel out, the only thing I have left are the meters per second, which is exactly what I want. So I take the 30 and multiply it by 1, by 1,000, and I divide it by 1 and by 3,600, or by 1 and 3,600, and it's multiplied by 1,000 divided by 3,600, you get 8.33 meters per second. So hopefully that's something that you've done before. If it's been a while, you'll get some practice, but it's not terribly challenging, hopefully. If it is challenging, don't be ashamed, just ask about it. You can ask me in my open math, you can ask me after class, you can ask me in class when you do homework, always. Do be aware that on Wednesdays after class I will not be available because I do have a class directly after this class that I teach, and then another one not long after that, so I'm pretty busy after this class on Wednesdays. But on Tuesdays and Thursdays I'm here for 3 hours.
I was going to ask about that metric system being related to water.
It is. So the metric system is actually based on water. Because, 150, 200 years ago, I think the metric system was developed just before Napoleon had his rampage through Europe. When Napoleon went rampaging through Europe and conquering everybody, one of the things he did is he made everybody use the metric system. He even tried to change the calendars and other things like that. Like the clocks and calendars he wanted to change as well. That was a mistake. But the metric system is a scientifically based system based on the science of biology, because that was the science of the time. 200 years ago, you had Pasteur, for example, in France. He was developing his method for pasteurizing milk. And what he learned is that milk wasn't being invaded by fairies when it turned sour. It was being invaded by microbes when it turned sour. And by slowly heating it up, it would kill those microbes. And so biology was a huge thing back then. And water, of course, is the basis of biology. Life exists where water exists. And so the scientists at that time said, well, all science is based on water. Well, we still use the system even though that's not really true. Water is by no means any kind of fundamental thing, but it is quite important for biology, and we allow that to be the case, and we still use it. The more you get into physics, the deeper you get into physics, the less they use the metric system. In fact, there are some realms of physics where they don't use anything in the metric system at all. The study of the universe, for example, is one. They don't measure distance in meters at all, meters per second. Meters, and they don't measure speed in meters per second. They measure distances in light years, because light is an absolute constant in the universe. The speed of light is constant everywhere in the vacuum. And so that is very scientific. And then for time, it's how far light has traveled, divided by, let's see. For time, they use they have a unit that deals with the light year and something else, I can't remember. But anyway, they derive their own unit for time. They derive their own unit for distances. Distances are all measured in units of AU, I think, essentially, in smaller distances. For long distances, it's some other thing. But they use measuring units that are much more fundamental, not related to something in biology. But you're right, that is. Because if you take a centimeter squared of water, that's a milliliter. A gram of water is a cubic centimeter of water. So it's all based on that. And if you take a chemistry class, you'll learn that in great detail. In my physics class, that's all we're talking about. It's interesting, but it's not really all that scientific, so all right, we have about 10 minutes to cover the last two sections. Shouldn't be that hard. So in physics, we do have to think about how accurate our numbers are, how precise our numbers are. We have to be able to communicate I'm going to teach you about that right now, but I'm not going to be a huge stickler on it after this first week or two, because there are more important things for us to be learning than how to deal with significant figures. If you go on in science or in mathematics or in engineering, you will learn more about this and you will get very specific instruction on how to use it in your field. But we will talk about it here just very shortly. So what is the difference between accuracy and precision? It's really quite simple. There it is. Okay? Which one's accurate, which one's precise? So this is precision right here, right? Precision means that your numbers are all very close to each other all the time. That you can repeat your experiment and get the same results every time. That's precision. And that has to do with very careful experimentation. That means you're very careful at what you're doing so that you get the same result every time. This one is accuracy. You've got something that you're trying to achieve, and you get close to it every time, but you maybe don't get the same results that you did this last time. Maybe your results aren't all close to each other, but they're all close to what you're trying to achieve. Okay? So that's the difference between accuracy and precision. Of course, we would like to have both in science. It would be great to have accuracy and precision. Accuracy comes from having a good theory and having a good model that fits that theory and having a good experiment plan that's going to test that theory or that model. But this comes from having good experimental practices, good methods, being, I guess, careful, right? Being very careful with what you do. Doing it the same way you can. Sometimes you can't help it. Sometimes, what are you studying? Pesticide application. So over there at the farm, he's getting his master's degree in farm English. They've got this wind tunnel that's like twice the length of this room. And at one end they have these sprayers that spray insecticide, at the other end they have a bunch of tomato plants that they're going to kill. And they spray the poison at this end, and the tomato plants at this end get sprayed downwind. But there's wind going all the time. Well, how precise can you be with that? It's a squirt gun in a wind tunnel. It's not going to be precise. And so what do they do to try to get precision? Well, they're very careful with the way that they have their spray nozzles. They're very careful with the way they put them in. They're very careful to measure the distances. They're very careful to place their plants. They use lasers to actually measure the spray to see what the spray is doing so that they can try to repeat that. And they do the experiment a million times. Well, not a million, probably do it like dozens of times. But the more often you do the experiment, the more you can adjust things to get precision.
That laser measure how unique is droplet size.
That's right. So you can measure droplet size.
The wind won't reflect it.
That's part of it. Yeah, the size of the droplet can make it deflect more, but the mass of the droplet can make it deflect less. So there's kind of a sweet spot. And that's part of what you're doing. They're trying to be precise because the farmers want the spray to hit the plant and nothing else. So that's what they're shooting for. And they adjust things until they can do it. And they test spray nozzles to tell these manufacturers, your spray nozzle is great, yours is terrible.
Kind of to oversimplify, one is how you do it, the other is what you do it with.
Yeah, you could think of it that way. But it's also what you're trying to do versus how well you do it. It's also, it also sometimes has to do with theory. Some things you can't do precisely. There's just some things that are that way. So you're looking more for accuracy.
Being precise has to do with the tools you have to.
It can be, yes, very much so. Yeah. So that's accuracy and precision, and of course, very, very important. But even more important than accuracy and precision is knowing how accurate or precise you are. Okay? So that's what we call uncertainty. The uncertainty is how much you know about how accurate and or how precise you are. So that will tell people what the limitations of your experiment, what the limitations of your equipment are. And to get a percentage of uncertainty, we use this formula which comes from statistics, where the percentage of uncertainty is equal to this delta times A. The A is your value or your measurement, your number, right? And the delta is how much it changes. That's the change from that number. So if your number is 12, and your measurement, if the number that you're trying to get is 12, and your measurement is 14, right, then the delta A is 2. If your number you're trying to get is 12, and the number that you actually get, your measurement, is 9, then your delta A is -3. And so on and so forth. Right? Now, sometimes you'll use positive and negatives up here. Sometimes it will always be positive. It depends on where you're using this. But this is the formula that's used. When you divide that by your number you're shooting for, multiply by 100, and you get a percentage of your uncertainty. Right? So, this here's an example of this where we've got 5-pound bags of apples, yeah? And they're supposed to weigh 5 pounds, but they don't. Some of them are 4.8, some of them are 5.4, and they're in between. So what we do is we're going to determine what is the uncertainty here, right? So the A is what they call the expected value of the weight, so that's our 5 pounds, right? And then we plug in our equations. Whenever we have a big group of numbers here, we plug in the largest number that the largest delta or the largest change, right? So this is our largest. They call it a variation. I don't know if they call it. The largest variation from 5 is the 0.4. So we have 5.4, which is the biggest change. So we put in that 0.4 as our delta A over our A, right? Delta A, you get the 0.4 over 5, it's going to be 8.08, rather multiplied by 100, you get 8%. So you have 8% uncertainty in your value. Now another way to do this is to use another way to do it, which is often done in science, is to use a plus or a minus. And the way that you do that is you take an average of these numbers, so you add them all up and divide by how many numbers you have, which is 4. So you add all these numbers up, you get something in the realm of 20, about 20-ish. You divide by 4 to get your average number, and then you would calculate usually what we call a standard deviation, which is not something we mess with right now, we'll see a little bit later. But the standard deviation is going to tell you the average change from the average. That makes sense? And then you would put plus or minus that average change from that average number. And that's another way of showing your uncertainty. It's actually a way of showing your precision. This is a way of showing your accuracy, and the other one shows you precision. So those are some ideas in science that we have to be aware of. Now we've got to talk a little bit about the significant figures. Have any of you encountered the phrase significant figures before? Yeah. So significant figures are kind of a strange idea that confuses the heck out of everybody until you use them for like 10 years. But it's a way of realizing what part of your number is actually precise. Because when you're doing calculations on your calculator is just going to give you all the digits it can. But your calculator doesn't know what your measurement was to begin with. It doesn't know anything except the numbers and what you know what to do. So I like to go back to my analogy with the aircraft carrier and the mouse, right? If you're trying to measure a mouse and you're using an aircraft carrier as your unit, and you don't have any units smaller than an aircraft carrier, you can't measure your mouse very precisely because the aircraft carrier is so much bigger than your mouse. So your mouse is one aircraft carrier. That's very precise. But that's all you got. But if you can start splitting your aircraft carrier into smaller pieces, half an aircraft carrier, quarter of an aircraft carrier, or a tenth of an aircraft carrier, or a thousandth of an aircraft carrier, then all of a sudden you can be more precise in your measurements and you have what we call more significant figures. Instead of having just a 1 aircraft carrier, you have a 1.001 aircraft carrier, or a 1.0001, or however small you've made that measurement device, right? So significant figures depend on the size of your measuring devices, and the precision of your measuring devices, but it also depends on the mathematics that you use and the other measurements that you have. So when you're doing mathematics, it affects what numbers become significant. So here's an example with addition. We have two numbers here, two measurements that are measured in kilograms, 7.56 kilograms, which gives us a number that tells us that they were able to measure this to 100 per kilogram. But this number tells us they were able to measure to 1,000 per kilogram. Now when we add these two numbers together, what kind of precision can we claim that we have? What's that? That's right, one that is least precise. And it's not as easy as you think, because here we say we have three significant figures. We have three numbers that mean something. Here we say we have four numbers that mean something. They have this one here too, 13.7. So we have actually a third one which says we have another three numbers that are precise. But we only count the numbers. We don't care that this one goes to hundreds and this one only goes to tens. We just care how many digits, how many different numbers we have that are measuring something to some kind of precision. So when we're done adding these or subtracting or whatever we're doing, the number that we get in the end, we have to start counting from the left side three numbers, because the best thing, the worst precision we have is three numbers. This one is 4. We call them figures. This is 3 significant figures, this is 4. And then we have to cut this one off, we have to truncate it after 3 significant figures. So even though this one's to hundreds, this one's to thousands, this one's cut off at tenths. And that's not merely because this one is cut off at tenths, it's also because these two are both at 3. So they have to cut it off. Well, actually, they're saying that differently. They're saying, okay. But that's fine, that's fine. I think I just explained one for multiplication too. They don't even do multiplication. No, this one is, sorry, this one is the other one. This one, you actually do look at you look at the decimal place. So this one has the least number of decimal places at 1. And so it's at 15.2, it's not counted. For multiplication, you have to count them. I apologize for that. So for multiplication or division, you count. Say this one has 3, and this one has 3, this one has 4, and you take the least number, and you count the 3 on your final answer. Because with multiplication, you can get all kinds of weird things. So you have to do that. But this one, you just look at the one that has the least number of decimals. So if you added 4 to this, then this answer would be 19, not 19.2. Because you wouldn't be able to take that decimal point. And like I said, we're not going to worry about it. I haven't used this stuff since I was a graduate student doing research. Because unless you're doing research, it just doesn't really matter much. Because in research, people are going to check your work and check your significant figures, and it tells them how precise your research is. But in class, I'm not going to worry about it because it just wastes time. The last section, which we'll cover in 2 minutes or less, is really quite simple. It's the art of lying mathematically. We call it approximation. My favorite example of approximation is the number pi and the number pi squared. What is the number pi? 3.1415, whatever it is, right? It's just this number. And is it closer to 1 or is it closer to 10? Closer to 1. So in the laboratory I work in, whenever we had pi in the equation, we would just call it 1. Because it's easier to do math. And we weren't trying to be precise with our mathematics, we were just trying to get a roundabout figure. We had 1 million atoms in our trap. We thought we had 1 million atoms. That was about what we were supposing we had 1 million. And so we did a quick calculation using some geometry and some densities and some temperatures, and we calculated. And we ended up calculating about 1 million. What does it matter if it's 5 million or 3.14 million? It's about 1 million. We're not going to go in there and count 1, 2, 3. We just needed to know about how many. So pi is equal to what? But in the same sentence, my professor would look at another equation and say, oh, there's pi squared, that's 10. pi is 1, pi squared is 10, that makes a lot of sense, doesn't it? But mathematically it does make sense. Because if something is very close to 1 and you're just approximating, just call it 1. But if it's very close to 10, you can't just call it 1. You have to call it 10. And they all kind of even out in the end and give you an approximate answer. So here's the great example. Can you approximate the height of one building on your campus or in your neighborhood? Let's approximate the height of the Empire State Building. Most famous building in the United States by far, right? How many stories is the Empire State Building? It's like 100 stories or something. I think they have I think there's 103 floors. Is that right? Let's look at it. Empire State. Floors. Let's look how many floors it has. 102. See right here, the 102nd floor is actually right up here. Nobody is allowed above the observation deck. The observation deck is as high as you can go as a normal person. But if you are like rich and wealthy or you're getting married, you can go up to the 102nd floor. This one's at like 90 something. But this right here, this picture is the 102nd floor, the 103rd floor. So that's the one you can only go to. And that's all you get, is that little walkway and this like little 2-foot balcony. And then, woo, right? But anyway, so 103 floors. It's 103 floors. How tall is it? Approximately. Let's do it in meters. So right here, this is a floor in a building. This is a normal building floor. Is that 10 feet? Yeah, it's a little longer than that. Yeah, I would say it's at least 4 or 5 meters. And the reason for that is all this ductwork and other stuff in between floor. So we're talking at least 3 or 4, let's say 4 meters. Yeah, 4 meters. So how tall is this thing? 400 meters, right? Pretty simple. You've just approximated here. Let's see how tall it actually is. We've approximated 400 meters. Empire State Building is 400 meters. Not bad, right? That's approximation for it. It's exactly 400 and something meters, but yeah, that's pretty good. That's approximation. If you want to approximate the thickness, let's see if I've got some. Here's one of my favorite ones. I've got these business cards. And if you, well, these ones don't do so well. My old business cards, it's really good. I have some somewhere. Let's do this. I've got to find my old business cards. I put them aside when I got me new ones, and I put them aside for anyway, I had these old business cards that had a thick ink on them. So when you squeeze one side of the business card, this stack of business cards that was about an inch thick, you squeeze one side and it was about an inch thick, but if you squeeze the other side that didn't have ink, it was about 3/4 of an inch thick. And the stack of business cards was 50 cards. So I had 50 cards, inch thick on one side where the ink was, 3/4 of an inch thick on the other side. How thick is the ink? Can you approximate it? 50 cards, 1/4 inch ink, right? You do that. That's approximation. Useful? Absolutely. Especially in physics. We're going to be dealing with all kinds of huge numbers and all kinds of little numbers. And if you're looking at all this math and you're getting the wrong answer every time, approximate. Look at the math again and just say, well, I've got a 50 there, I've got a 12 here, I've got a thing here. Let's make that 50, but leave that as a 50, but the 12 will be a 10, and this one will be this. And you just approximate and say, where should the number be about? And your number's off by a factor of 1,000. You've made a math error, right? Or you've got a number in there that's goofy somewhere. Something's wrong. And so approximation is important. But even more important than approximation is knowing where your numbers should be in physics. If you're doing a math problem talking about, traveling from point A to point B on the way to school or something, and you get 38,000 meters, there's something wrong with that, right? Well, if it's a short distance, you get 38 million meters, there's definitely something wrong with that, right? You want to make sure that your answers are matching the problem, so that you're not just putting in answers and assuming they're right without thinking logically. And approximation is a big part of that. So we'll leave it at that. We're done with chapter 1. Go ahead and get started on the homework. When we come back tomorrow, we'll answer questions about the homework after we get through with it. And then hopefully we'll get started on chapter 2 as well. And we will see you all
Are you
later.
calling homework one quiz on open?
I'm sorry?
Are you calling homework one quiz on open math?
What do you mean? My open math?
Yeah.
On my open math, the homework is right here, chapter 1. Yep. So this is chapter 1 homework.
All right, click on number 2. When you were there, no, not chapter 2, number 2.
This one?
No, go back to number chapter 1. Number 2.
Question 2.
All right. Now we want to just looking at it like another one is T. How do you figure out what the base unit is? Because there's only 4 units, right? That we're using. We're trying to convert everything down to the 4.
No, not necessarily. No, you're just converting it into another like unit. So if it's in meters per second, they want you to go to miles per hour. Those are like units because they're measuring the full speed. Right? In this one, you're just converting to meters. And that's a micrometer, right? So that's in there. And the standard unit is meters. So how many meters is 4.8 micrometers? We do the conversion. There's 1 million micrometers per meter, or 1 meter per million micrometers. And then you do that conversion unit. But go ahead and give it a try. If it's not working for you, if you're not understanding it from reading the book or watching a video or something like that, bring your question tomorrow and we'll work on it in class. We'll use class time tomorrow to work on the homework. But at the moment right now, I got to go teach another class. So, all right? You're welcome to stay in here if you'd like to work on homework. I will be in another room. So.
this is easier.
System ranks these from largest to smallest. I have no idea what Western Wall is. So I'm gonna make it up.
Yeah. Pull up that thing he had, the useful, you have to open two windows, but open one up, that is the useful tool, and the other one is the tool.
get it, good.
Just enter prompt.
Anybody gets the 2.9 G in, I'm curious.
G in?
Yeah. The number 2, Q2, 2.9 G in.
Capital G?
Yeah.
Giga Newton? Because we got millinewtons on ours.
Okay.
I don't know, it's all messed up.
Yeah, because I tried to put a unit in, right? And
I don't know.
I don't have it.
Oh, okay. Like ours is all different.
Yeah, I'm gonna send you guys to.
Oh, you are? Oh. You got other classes? Other math classes? I was gonna take some trig, but I talked to him, he told me, yeah,
Dude.
teacher, here.
Yeah, I just finished the period last semester.
Oh,
take it logging down.
Robin Valentine's be easier.
Julie's, that's good, minus three.
Oh, I guess.
I just would be divided.
Oh, I'm writing it out. I think so. I think that would be
Seems so.
still not sure?
No, I think.
Oh, I see. I see.
It looks weird.
What do you write everything out? I can. I didn't write it down, I probably should.
That's kind of confusing.
Yeah. What did he say about notes? You can't use these notes for the test?
Generally, use notes from book.
Except in both tests, it's not there.
No, nothing.
Oh. Is your username for Wi-Fi your whole email address?
This stuff is, the numbers.